where's his grandma's shoes?
No, we don't have the same size.
Okay, so we are going to talk about solutions again today. So,
I mean, you can. No, you can't.
Just hers.
Yeah.
What size shoe do you wear?
I don't know, 13.
so water molecules are polar, right? You guys know that. They have, well, we talked about polarity, and we talked about how if you had a molecule, so this is a water molecule, okay, and how if you have lone pairs of electrons on that central atom, you're always going to have a polar molecule, okay? We talked about shape with this. We call this a bent structure. We said that this end, yeah.
Where is this?
Right here,
Where's that?
somewhere in the middle. Just keep flipping.
Oh, I'm confused because there's solubility notes, so that's not it. Okay. Where is it? Whoa, it's here.
Just keep flipping pages.
It's weird. Wow, okay. We're good.
Third page from the back.
So third page from the back are where the notes are. If you're having trouble finding them, I apologize. Apparently I got the packet out of order. Imagine that, me making a mistake. It's so unusual. All right, so like I was saying, we have water molecule here. We have these lone pairs of electrons. We have our hydrogen here. Oxygen, remember, is a very highly electronegative element. What that means is that it's going to kind of hog these electrons. Okay, so the electrons are going to be around the oxygen more than they are the hydrogen. So that gives this end of the water molecule a positive charge and this end a negative charge. Oftentimes that charge is represented with symbol like this. This is some sort of Greek symbol, I believe. I don't know what the name of it is. Other times you will see it drawn like this, where they have an arrow pointing towards the negative end, and the positive end then they'll denote with the back side of the arrow making a positive sign. So that means that this end of the molecule is negative, this end is positive. Okay, so water has that partially positive and negatively charged end, and because of that, it will have intermolecular forces with another water molecule, where the positive and negative ends of that water molecule, the positive end of this one will be attracted to the negative end of this one, and we call that an intermolecular force. Because this is a polar molecule, this has not only LDF, it also has dipole-dipole and hydrogen bonding, because this is oxygen with a hydrogen attached to it. Okay, so we've got hydrogen bonding here. So this is going to be a fairly strong intermolecular force compared to some other substances.
That's cool.
All right, we're in constant motion because we have the kinetic molecular theory. If we are ice, then we're just vibrating in place. If we are water, then those liquid molecules are able to slide past one another, but we still have this intermolecular force. And then, of course, with gas, the particles are spread apart too far for that intermolecular force to take place. All right. So when we're talking about things being soluble and insoluble, what happens is when you've got a crystal over here of like sodium chloride, and we learned this back when we were talking about ionic compounds, you've got these alternating positive and negative charges, okay? These also have an attraction between them. So there's an attraction between these positive and negative ions, okay? If that attraction, so if this purple attraction here, if that is less than the attraction between this and this, then this item will be soluble, because what's going to happen is you're going to end up with one of these, or, well, eventually all of it, but you're going to end up with this coming in, and these water molecules are going to orient themselves in such a way to surround these ions. So for example, if we had our sodium here and a plus, this is a positive ion, so the negative part of the water is going to get attracted to that positive ion. And you'll end up with that positive ion surrounded by these water molecules. Okay, so that surrounds it. And then conversely, with your negative ion, the hydrogen end of the water will surround it. Okay, but the attraction here between these water molecules and the chlorine, or the water molecules and the sodium, this has to be bigger than this attraction here. Okay? If, for example, you had something like Ag plus Cl minus, okay, that attraction, I'll do blue here, this attraction here between is going to be greater. And if you go back to this fancy dancy chart here, remember this guy?
I do.
Okay, the ones that had N in them meant that they were not soluble. Well, this is a not soluble one. So here, this attraction is going to be greater than the attraction for the water. So this is going to stay together and it'll stay as a precipitate. They're more attracted to one another here than they are attracted to the water molecules. Does that make sense?
Yes.
All right. So eventually, all of your ions are going to be distributed evenly among the water. Now, a couple different cases can happen here. Okay. Case number one. Hey, Austin, can you see if you can find some sodium acetate? It's in the last, it's over by the metals. I usually have a flask in there that has some of it in there that I just need to heat and get it in the solution. So I'm going to see if I have that demo still from last year. It's kind of one of these reusable ones, and eventually you have to remake it. I can't remember if I threw it out last year or if it's still sitting back there and we can regenerate it. All right. So there is a condition called a saturated solution. When you are saturated, what that means is you have less water molecules than you have. Yep, that's the one. And let's see, I'm going to need a hot plate too. Add 30 mils, and I need 30 mils of water apparently.
At least you left yourself. They look like dish soap.
What? Oh, yeah. I thought you were.
Let's see which one cleans the dishes for them. Which beaker comes out for you?
Well, the last one's water, so we can just use that.
Just drink that.
Yeah, but I don't, that won't get it clean.
I know, that's why we don't need to use that.
Oh, I thought you said we should. I'm like, what?
What are we going to do next year without you?
So, me?
And you're going to be back. You're coming back.
It's fine.
Look it, I'm drawing circles. Look it, I'm drawing
Just
circles.
have us instead. Do a job here.
Yeah, Austin, you can't graduate. I do.
Yeah, just fail him.
Just make him your.
Yeah, because I give him a grade right now. Right.
Good point. Give him the fails other classes.
Yeah.
You're a teacher, you get connections.
You know, graduate. Your mom would love me. All right, we'll see where that goes. Check back on that. So we'll see about that sodium acetate and see where that goes. All right, so let's keep going here. So a saturated solution is where you have less water than you have solute. All right. Unsaturated then is the opposite. We have more water, so we have leftover water compared to the ions that it's trying to break up. And then we have something called a supersaturated. So at a given temperature, normally your solution can only hold so much, but there's certain things like this sodium acetate that we can actually get to supersaturate. So what you can do is you heat this up to a high temperature and then you let it cool, but it's very unstable. So just adding a small crystal of that in, or sometimes just tapping the side of the container, it'll cause it to seize up and look like what it does right now. Okay? Because it's so unstable. So that's what a supersaturated solution is.
You have to wait till it dry before you erase it.
So like when it's saturated, there's just no more space between the water molecules.
Mm-hmm.
Oh, that's right.
All right.
Okay, now it just printed weird, I think.
Okay, yeah, well, it's probably I'm sure it's my fault so see if you can find and locate this in your packet.
Well,
This is right, this is in order. That's what I was
Yeah, I
looking
think
at.
it just like printed.
Yeah, well, like I said, Lippy screwed up. I know, you're surprised. So solvation then is the process of
Your name, salutation,
solvation.
Salvation.
salvation,
Salvation. No.
salutation.
No.
No.
I just like saying some words. I know it's salvation. I wrote salvation.
So solvation is the process of mixing these solutes with the solvent and you're forming a solution. Solvation in water then is called hydration.
Oh. That makes sense. Little chemist. Who made chemistry?
Lots of people.
Well, I don't know, because Isaac Newton made calculus, and then who made chemistry?
Oh no, Lippy did not make chemistry.
What are you talking about?
Lots of smarter people than Lippy. Lippy just copies and disseminates out back to you. All right. So during solvation, the solute must separate into particles and move apart. This requires energy. The overall energy change that occurs during solvation formation is called, what do you think that is? No? What do you think I was trying to get at here? Heat of solution. There we go. Good old Google.
That's what I was thinking, but I wasn't sure. Like, yeah, maybe it's from.
I would agree with that statement. This is spooky.
All right. So agitation then, which you could stir or shake. And you do this a lot of times in cooking. I mean, think about when you're trying to cook things, okay? Trying to get things to mix together. You're agitating them somewhat. The thing in your washing machine that like moves back and forth, you may not be able to see it anymore. Sometimes they have the clear things and you can see it and it's moving back and forth and back. That's called an agitator, okay? Because it's mixing things. It's mixing your clothes with the detergent and the water that's in there and hopefully knocking some dirt off in the process, right? That's what you're hoping for, okay? So what that does is it's going to allow these surfaces to make contact and make new collisions and increase that rate of solvation, okay? Grinding, where you're breaking the solute into smaller pieces, that's going to be increasing the surface area. It's going to allow more collisions, and that's going to increase your rate of solvation.
Chemistry is such a wacky thing.
And then heat.
Oh.
So almost all solid solutes, as temperature increases, that rate of solvation will increase too. This is one reason why you heat things on the stove, is to get them to mix together better. Okay, does that make sense? Now, this is going to require you to kind of warp your brain a little bit, because this isn't intuitive. This you have seen in action, okay? This, however, these gas solutes, as temperature decreases, the rate of solvation increases, okay? Have you ever had warm pop?
I think so. I like warm pop. I don't drink anything but
Okay.
Sprite. But
So I'm trying to get something that you guys have had some experience with. That's why I bring that up, okay? Warm pop will lose its fizz much faster than cold pop, okay?
Yes,
so it's not gonna, for those of you who enjoy the dissolved carbon dioxide in pop, it will have less gas dissolved in the warm versus the cold.
Does that mean it's better?
I don't know that it's better for you. I mean, you typically will burp out the CO2 anyway. So, I mean, you know, when you drink pop, you oftentimes have to burp anyway. So get rid of some of that gas.
What's your favorite letter?
Now, environmentally, where this comes into play, I mean, it comes into play a lot of places environmentally, but with fish, for example, okay? What do fish use for respiration?
Air.
Oh.
Right, they use gills in their, you know, in the fish itself, but what are they getting in? What chemical are they bringing in that they use? Oxygen, okay? So they're getting oxygen just like us. Where do they get that oxygen from? Do they take a water molecule and split it apart and pull that oxygen off? No, they do not.
Fishes are pretty positive.
Okay. In your water, okay, so let's say that these are your water molecules here. Okay, these are your H2Os. Okay, interspersed or dissolved, just like your pop. Okay, your pop has CO2, but in this water, you have oxygen dissolved as well. So you get to climates that are warmer, and you're going to have less oxygen dissolved for those fish. Or you get to the middle of summer and it's really, really hot, hotter than it normally is for that climate. There's less oxygen for those fish, and those fish are used to having more oxygen. You oftentimes will have fish kills. Okay? This is also why if you have a fish tank, you typically will have a thing that's bubbling in, like the water runs through it and it kind of bubbles in air. Okay, that's so that the fish can have oxygen to breathe in that water. Okay, You'll also see different species of fish having different demands for this. So like your freshwater, like trout and salmon and that sort of thing, the things that live in colder climates, they have higher oxygen demands than the fish that live in warmer climates. Because the ones that live in warmer climates will not survive if they have those high demands because there's not as much oxygen dissolved in there.
Okay. What's my favorite consonant? What's an easy one?
Is there a difference between solvation
They're
and
my
just dissolving
favorite.
something?
No.
They're just different ways to
Pretty
say it.
tough. What? No.
All right. So solubility depends on the nature of the solute and the solvent.
Because why is the glue? Because it's only.
Did I repeat this?
It's like rare.
No, I didn't.
No.
No, this is fine. Okay, but I'm repeating terms here because this is unsaturated again.
Oh yeah, you did repeat this.
Yeah.
Because this was on the weird page.
This
That was
is on the-
printed weird.
This isn't how it was.
It's worded different.
And this is saturated then. I guess it's just a good review. Who knows what Lippy was thinking.
I asked that.
Well, if you hear it twice, you'll remember it better.
Yep.
It's true. You're more likely to hear it twice. Wait, gosh.
And this is
That is so
increases.
That is so weird.
Again, just kind of. This is repeated again. I don't know what I'm doing here.
I don't know. This one has a problem
Yeah.
at the bottom.
Solubility of gases. That's new.
Henry's law.
Henry shared it?
No, I don't know. I don't think so.
Yeah, Henry shared it in my class in 6th grade.
Oh.
Oh, because this one talks about pressure too.
Yep.
He was driving his corn.
Okay, Henry's. I gotta just make sure that I'm thinking of this right. Okay, yeah, it is proportional. Okay, I was thinking of it right. Okay, so solubility of gases decreases as the external pressure is reduced.
Oh, I thought it was proportional.
It is proportional. If this
Oh, I
goes
thought
down,
you-
this goes down.
I thought you meant the
Okay.
box was.
So for example, with your knuckles, okay, there's pressure in between your knuckle right now,
Really?
okay? And in that knuckle, there is some fluid called synovial fluid. That's what kind of lubricates your joints, okay? If you take, and I'm not telling you to, so if your parents have told you not to pop your knuckles, don't do it. But if you take that and you reduce that pressure by opening up that joint, okay, that is going to cause that gas to come out of solution.
My mom said if I crack my knuckles, it would help give me arthritis.
And that's why I told you not to do it. I'm not saying, I'm not coming down one way or the other. What I'm doing is I am explaining to you why your knuckle pops. What you're hearing there is that gas coming out of solution. So when you reduce the pressure on that knuckle, okay, that gas comes out of solution because like we said here, the solubility of gases decreases as the pressure is reduced. So you reduce the pressure, that gas comes out of that synovial fluid.
What are you saying that
Okay.
it does?
I'm gonna be honest, I don't know how to
I'm not coming down one way or the other on the arthritis debate, okay? I'm explaining to you what's happening within the joint.
I don't know
Okay.
how to crack my knuckle. I don't know
So,
how to- Ew, don't do
When
it.
you crack your knuckle, it comes out of solution. The other thing that you hear this with is pop, okay? When they bottle pop at the manufacturer, they bottle it under pressure. Okay. So when you go and you unscrew that pop, you're making it the same pressure as atmospheric pressure out here. Okay. You've reduced the pressure. What happens to some of the fizz in that pop?
Okay.
it escapes. That's the that you hear. Okay, it's the pressure equalizing, but it's also some of that pop coming out of solution. And I think that's all the notes I have for you.
It is.
So you are going to go to a couple different websites today.
We're going on an adventure.
Yes, you are. And you are going to be discovering, and I got to get those links up for you. You're going to be discovering a couple different articles that are going to talk to you about solubility.